This is lesson 10, electrolysis. So an electrolytic cell is different than a voltaic cell. An electrolytic cell is when an external source of voltage, so some power, is used to cause a redox reaction that would not normally occur, that would normally be non-spontaneous. So in an electrolytic cell, you have an electrolyte. So the electrolyte is the reactant when you have electrolysis. And it's a liquid, and the electrodes are where the redox reaction occurs. So the electrodes remove the charges on the ions and form products that are neutral elements. So ions are discharged in electrolysis, and electrolytic cells are used to separate many non-reactive metals from their ores. So when you pull an ore out of the earth, a lot of times to purify that metal, an electrolytic cell is used. So here's a picture of an electrolytic cell. An electrolytic cell has a few components. The first is that a battery is required. So here's the battery in the middle of the wire. And the second thing in an electrolytic cell is that the electrodes cannot touch each other. So you can see that here it's only in one beaker, whereas in voltaic cells we had 2 beakers. Here you only need 1 beaker, but the electrodes cannot touch. The third part or component of an electrolytic cell is that electrons are pushed towards the negative electrode or the cathode. So just like in the electrolytic cell, the electrons are going from the anode to the cathode. And the electrons are being released at the anode, the positive electrode. Now, instead of a salt bridge, ions are transferred through the solution itself, because remember, it's only in 1 beaker. So the negative ions are going towards the anode because that's what's losing electrons, and the positive ions are going towards the cathode because that's what's gaining electrons. So let's just summarize real quickly the difference between voltaic and electrolytic cells. So in voltaic cells and in electrolytic cells, the anode is oxidation. Okay? However, in voltaic cells, the anode has a negative charge because it is losing the electrons. In electrolytic cells, the anode has a positive charge. The cathode in both voltaic and electrolytic cells is where reduction occurs. In a voltaic cell, the cathode is positive, but in an electrolytic cell, the cathode is negative. See how it's connected to the negative terminal of this battery? So the products of electrolysis. To determine the products in an electrolysis reaction, the first thing you have to do is identify all the ions present in the electrolyte and determine which one will migrate to which electrode. The second thing you need to do is where there's more than one ion at each electrode, you need to determine which will be discharged. So you have to write the half equations at each electrode. Next, you balance the electrons lost and gained, and then consider what charges would be observed in the cell as a result of the redox process. So let's watch a short video about electrolysis.
The Earth's crust contains many compounds, but the compounds themselves aren't as useful to us as the elements they're made up of. This rock contains aluminium oxide. Split the aluminium from the oxygen and you have one of the world's most useful metals. You can split a compound using electricity. The idea is to pass an electric current through it, a process known as electrolysis. Circuit set up using 2 carbon electrodes, an ammeter, and a power supply. The white powder is lead bromide. Switch on the power supply, and nothing happens. The ammeter reads 0. Solid lead bromide doesn't conduct electricity. It needs to be molten. Lead bromide melts at 370 degrees Celsius. Switch on now, and a current flows. In this circuit, the electrode on the right is positive, the one on the left is negative. As electricity passes through the molten lead bromide, chemical reactions start. On the left, at the negative electrode, nothing appears to be happening. But at the positive, bubbles mean a gas is being produced. Placing small tubes around the electrodes traps any gas, making it easier to see their colour. What could the brown gas be? The gas is bromine. Although nothing obvious appears to be happening at the left-hand electrode, pouring the molten lead bromide away reveals a small silvery metallic bead. This is pure lead. So, passing an electric current through molten lead bromide breaks it down into the elements lead and bromine. To work out why this happens, imagine you can see the charged particles, the ions, in the compound. There are positive lead ions and negative bromide ions. Once the power supply is switched on, the lead ions are attracted to the negative electrode. The bromide ions are attracted to the positive electrode. Lead ions pick up electrons. They lose their positive charge and form lead atoms. Bromide ions give up electrons. They lose their negative charge and become bromine atoms. These form a gas. Electrolysis of lead bromide only works when the compound is molten. Why doesn't it work when the compound is solid? Change the compound from lead bromide to zinc chloride, and the products of electrolysis will be different. What would you expect to see happening when electricity is passed through molten zinc chloride? This time, bubbles of a very pale gas appear at the positive electrode. It turns damp blue litmus paper red and bleaches it lighter. So what gas is it likely to be? Again, nothing appears to be happening at the negative electrode on the left. But pouring off the molten zinc chloride reveals a bead of pure zinc. In industry, electrolysis is carried out on a huge scale. Massive amounts of electricity are used to extract reactive metals, like aluminium, from their ore.
So after watching the movie, here's a picture of the electrolysis of sodium chloride. So again, you have molten or melted sodium chloride in solution, and you have the two electrodes. So you have the negative electrode and the positive electrode. The chloride ions will be attracted to the positive electrode, where they will lose their electrons to become chlorine gas. The positive sodium ions will be attracted to the negative electrode, where they will gain electrons to become sodium metal. So what would you predict to see in this reaction? If you said sodium metal forming and chlorine gas bubbling at the positive electrode, then you're correct. So, the number of electrons. Coulombs is the amount of charge passing through an electrolytic cell. So 1 mole of electrons passing through a cell is 96,485 coulombs. And this number is called Faraday's constant. A coulomb is equal to an amp times a second. Here's an example of a problem involving the number of electrons. Calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 amps. So, the first thing that we know from the problem is that aluminum is being formed from aluminum chloride. So the reaction that we're concerned about, the reduction of aluminum plus 3 to aluminum Al. And we know
that 1 hour has 60 minutes in it, and that there's 60 seconds in 1 minute. So we know that 1 hour is 3,600 seconds. So if a coulomb is an amp times a second, we know that at 10 amps, 600 seconds means that there are 1,000 coulombs passing through this reaction. Well, we know from Faraday's constant that 1 mole of electrons is equal to that special number, 96,485 coulombs. And in this reaction, if we look at our balance equation, we need 3 electrons to form a mole of aluminum. So electrons to form 1 mole of aluminum. And that will give us 0.124 moles of aluminum. But the question asks the number of grams. So we need to take the 0.124 moles of aluminum and convert from moles to grams of aluminum. So the molar mass for aluminum is 26 grams. And so we put this in our calculator and we get 3.23 grams of aluminum in that 1 hour.